Hey gang, welcome back to Biostat. Today we're going to talk about a few other non-parametric tests, the Wilcoxon signed rank test and the Mann-Whitney U test. We'll start with the Mann-Whitney test, and then we'll talk about the Wilcoxon signed rank test a little bit later. The Mann-Whitney test is also known as the Wilcoxon's rank sum test, or some people just refer to the test overall as the rank sum test. Okay. It's a non-parametric test to determine whether two population medians are equal. Notice we're not doing population mean right here. We're doing population median. All right. It's the non-parametric alternative to the independent two-sample t-test. And sometimes it's described as the test to determine whether two populations differ, because they're looking at the median here rather than the mean. They're looking to see how the data spreads out from the median, how much different the two sets might possibly be. Okay. The single advantage of this test, being that it's a non-parametric test, is that it doesn't require the assumption of normality. So our data for both of our groups don't have to be normal. Remember when we ran the independent two-sample t-test, one of the requirements was that both groups had to be approximately normal samples. Our samples drawn from a approximately normal distribution. Okay, so that's an advantage here. We don't have to worry about the assumption of normality. The disadvantage of this test, though, is that the null hypothesis can often be falsely rejected, especially when the two populations differ in shape, even if their medians are equal. So you could have two groups where the medians are roughly equal, but because the populations are such different shape, you'll reject the null hypothesis saying the medians are not equal. That can be somewhat of an issue here. It's not something you should really worry about. But again, if you prefer your data to be normal so you can run an independent two-sample t-test, because it's more powerful than this test in general. This test, the Mann-Whitney, aka the rank sum test, is based off of ranking the actual data values. So to rank these values in the two samples, we have to do the following things. I'm not going to make you do this by hand, but I want you to see how the ranking process works. Okay. All right, so you have your two different samples. You're wanting to compare them. They're similar measurements. So you put them all together into one large group. All right, you kind of put them together. The smallest value in the group, you put them in order from smallest to largest. The smallest value gets rank of 1. Second largest value, the next larger value gets a 2, and so forth and so on. So you're ranking them from smallest to largest in the data set. If you happen to have several data values in your two data sets that are the same value, or in other words, their ranks are tied. In other words, their ranks will be tied, even though we've preliminarily given them different rankings. Once we look back through, we'll see that some of the data values may have the same value, and therefore we have to assign an average of the corresponding ranks that go along with those things. I'll show you an example here in a minute of how that works. The groups are then separated back into their based with their corresponding ranks. They're separated back into the two separate groups, and then you sum those values in the two groups, and those sums of the ranks are what you use to come up with what they used in their formulas for this test to determine if there's a big difference between the two groups or not. We won't do that part, but I do want to show you on the next slide how the rankings work and how the ties and rankings work. So the way I've got this table set up is I've got the heights of children from two different groups collected, so 5 each, and so the heights are in inches, and I've got them listed in increasing order in the table below. So for all we know, maybe we're comparing the heights of these two kids based off of some vitamin supplement maybe they take that maybe improves their height overall, and maybe one group's taking one type and another one's taking another type or something of that nature. When I listed this out in the table, my column here, I kept it as group 1 or group 2. So that's just reminding me what groups these belong in. The actual data values that were collected are here in the heights. So that's 45, 3 46s in a row, so there's some ties. 48, 49, 50, a pair of 52, so there's another tied data value. And 54. These pre-ranks here are the initial ranks that you just do literally 1 through 10 in this case. So you just number them that way. Now the actual official ranks for these guys are going to go as follows. You're going to get a rank of, if there's no ties, the final rank's going to get the same rank as the pre-rank. So in the case of the first one, it's going to stay 1. It didn't have a tie. The second, third, and fourth pre-rank, the triple 46s there, are tied, and they're 2 through their original pre-ranks were 2 through 4. So we need to find the average of 2, 3, 4, which is just going to be 3, because 2 plus 3 is 5 plus 4 is 9, divided by 3 is 3, or the midpoint, if you will. So all 3 of these get the rank of 3. The value of 48 had a pre-rank of 5. There doesn't have a tie, so it gets a 5. Same thing with 49. It was pre-ranked at 6, so it stays 6. 50 as well, stays, its rank is 7. 8 and 9 here are tied because they both had those data values were 52. So we average the 8 and the 9 together, and that's just going to be 8.5. So both 52s get a rank of 8.5. That's what happens if you have ties. And the last one stays 10 because it didn't have a tie. The 54 didn't have a tie with it. So if you were doing this by hand, and I'm not going to show you the formulas again, but the general idea about this is you break these apart into group 1 and group 2, and you find the sums of their ranks. So for group 1, we've got this rank of 1 here, rank of 3 here. I'm looking at the top row here to kind of look back down at the rank. 6. Both 8.5s were in group 1. And so we take 1 plus 3 plus 6 plus 8.5 plus 8.5. And we'll sum those guys together. And let's see what I get here. 27 is the rank sum there. For group 2, we take what's left, and we've got 3 plus 3 plus 5 plus 7 plus 10, and that gives me a total of, let's see, 28. So the group 2 is just slightly higher in its rank sum than is group 1. What they do usually by hand in this test is they take the group 1 sum, the smaller, whichever one's smaller, and they use that to create a weird, like, sort of like Z statistic from the, like, and they treat it like a normal curve, so to speak, so that they can get a p-value for it. We won't be doing that here. As a matter of fact, I do not want you doing this by hand for any reason. We're going to let R do the work for us. So to perform the Mann-Whitney procedure in R, you want to start out. Step 1 is always perform your assumption checks, just like you would for an independent samples t-test. All right, we want to run the box plots to kind of look at what our data looks like there. Run the QQ plots with the QQ line, and maybe the Shapiro test, and we'll do that for each of the samples in our study. If the assumptions of normality are met, if our normality assumptions are met, then we go ahead and we do the independent samples t-test because it's more powerful. If not, if either one of the data samples of data looks not normal or shows non-normal behavior, then we move on to step 2, and we're going to run the Mann-Whitney U-test. So step 2, we just state our null and alternate hypothesis for the Mann-Whitney U-test. In this case, they use little m here. That's important to represent the median. instead of mu. Remember when we did this test here, we used mu, which is the Greek m, but it stands for population mean. Little m just stands for median. So you're just comparing them like we did with any of our other, when we did the 2-sample t-test, but you're using the median instead. So for the left tail test, your alternative is that the median from group 1 is less than the median of group 2. Your alternative hypothesis for the right tail is median 1 is greater than median 2. And if you do a 2-tailed test, this median 1 is not equal to median 2. And then you just run your Wilcox dot test to check for see if there are any significant differences between the groups and get yourself a p-value, just like we've been doing with every other hypothesis test, and you write a conclusion based off of that. So without further ado, let's do one of these and let's look at the procedure here. So in example 1, this study investigated how pollen removal varied with reproductive caste in bumblebees. Some cats named Harder and Thompson in 1989 recorded the proportion of pollen removed by 35 bumblebee queens and 12 worker bees. So we got 12 worker bees. The researchers wanted to show that the median proportion of pollen removed by the queen bees was less than that of the worker bees. So we need to first of all get the data into R. And we can just list these as vectors. You can put them in a data set if you want, but often this is just as easy to list out the 2 vectors of data if you've got them at your disposal. And so in R, I'm going to grab my data and throw it in there so we can get it in there. And I called one vector queen for the queen proportions of pollen removed, and another one with 12 proportions of pollen removed by worker bees, the data, and we get it on in there. So the next step, we know, as usual, we'd probably have to run a box plots to look at how normal the 2 groups look, or at least one step in that. So we're going back to the way we used to do box plots, unlike what we were doing with the ANOVA notation inside the box plot function. We're actually going to use the box plot function again. We put in both groups, queen and worker. Doesn't really matter what order you put them in here. And then I had to put in a names vector in here so that I would get the names at the bottom of my 2 box plots. And I just did a Q and a W there. All right. And so looking at those box plots here, we see there's an outlier in the worker bee box plot. That's one thing I noticed off the bat. The other thing I noticed is that the median line, the medians are obviously different in these 2 groups. The overall shape between the 2 groups looks pretty consistent to me, but where the medians fall are definitely not the same. Don't look like they're going to be the same. Both of these box plots, I would call them, mildly left skewed because they have a longer tail at the bottom, and they look okay upon first inspection. But we might need to run the QQ norm and Shapiro test on each of these groups as well to be sure. So let's look at the queen first, and then we'll look at the slide containing it. So I'm going to run a QQ norm and a QQ line plot here for the queen. And that's not a bad looking plot there. It's a little wavy in parts, but it never really truly curves too far away from the line. All right. And then I want to do the Shapiro test on that queen vector as well. That set of data. And it gives me a p-value of 0.1297. Now it's almost not normal. It's almost below that 0.10 mark we like this, that we use as a cutoff for the p-value. But all in all, that's not bad. I'm kind of okay with that, and there's not enough evidence to prove that that's not normal, even though it's kind of wavy. Okay, and that's pretty much what I've written here. This is not a bad looking plot overall. The Shapiro value is greater than 0.10, so we can call this approximately normal, or pretty roughly normal, if you will. Let's do the same thing, but for the worker bee group. Here's the output from the worker bee group. So I did the same stuff, except for I put in worker here at the very beginning of each one of these. And you see here that the p-value is 0.035, roughly. But then we've got this very curvy looking line around our QQ line. There's definitely something wrong with this. It's not normal. 0.03 is less than 0.10. So the worker data is definitely not normal. We can't use the independent samples t-test here. So we should use the Mann-Whitney test to compare these examples. Okay. So, stating your null and alternative hypothesis, we wanted to show that the median of the queen bees was less, the median pollen proportion taken in by the queen bees was less than that of the worker bees. And so my alternative hypothesis is the median of the queens is less than the median of the workers. Then my hoe here is the median of the queens is greater than or equal to the median of the workers. And in R, we're going to run the Wilcox.test. You don't have to load any specific packages for this, but I will tell you a little bit about what's going on in that function real quick. So I'm just going to bring it over here from my notes real fast, and then we'll talk about it. So Wilcox.test, you got queen and then worker, so your two groups. Alternative equals less. Okay, so you can do alternative equals 2-sided less or greater in this option here. So you need to know what your alternate hypothesis is. The exact equals false. This one will change your p-value to having either a continuity correction or not having a continuity correction. It's a minuscule difference, so I'm not really concerned with whether this is false or true here, but false is what I set it on, just out of preference. And then confidence interval I have equals false, because you can have it spit out a confidence interval for the median if you want, between the difference between the two groups. And so you look at that p-value, and that sucker is pretty small, 0.0003 for the most part. So what can you conclude from this test is this: since the p is less than 0.001, we reject the null hypothesis. There is very strong evidence that the median proportion of pollen removed by the queen bees is less than the worker bees, with a p-value of 0.0003. Okay. I would never ask you to do this, but some people might want to do this if you're ever doing research. If you wanted to find the confidence interval here, it's just as simple as bringing that thing back up by hitting your up arrow and then going here for confidence interval equals false, change it to true, and it will spit you out a one-sided confidence interval, which again, I can't iterate enough, you don't really want. So to really get a true confidence interval, we need to change the alternative to a two-sided version. Now, notice these are both negative in the confidence interval, which implies we put queen in before worker. That means the worker had just like our two-sample t-test interpretations, we would say that the population median for the worker bees is greater than that of the queen bees by at least 0.12 or 13, and at most 0.37. Okay, so that's how you would interpret that if you wanted to do so. But that's all I'm going to say about that. I don't see too many people running confidence intervals on medians. So, but it's not that it's not done. It's just I haven't seen it very often. All right, that's pretty much it for that test. So let's talk about the Wilcoxon signed rank test and a little bit about its background. So Wilcoxon's signed rank test. Wilcoxon's just some status guy who was a statistician. I don't really know as much about him as I do some of the other statistics guys. or just sometimes people call this just the signed rank test, is a non-parametric test designed to determine whether population means differ when the data is in the form of paired samples. So this is basically the non-parametric version of the paired samples t-test. You find your differences between your two. You have like either a before and after shot of data sets where you maybe measured something before from a certain group of people, and you took the same group of people and did something to them and recorded something after, and then you find the differences to get one sample of differences, and you use those differences. Now remember, when we did the paired samples t-test, those differences had to be normal. So if those differences aren't normal, then the Wilcoxon signed rank test is the way to go. So an advantage to this, again, just like the Mann-Whitney test, is that we don't need the requirement of normality here, so we can get away with it. But again, it's not as powerful as the paired samples t-test if the data is normal. The disadvantage of this guy is there's an assumption of symmetry here, that your two groups are similarly symmetric, or that the data set's somewhat symmetric. It doesn't mean it's normal, but that it's somewhat symmetric. And being symmetric is a little less restrictive than normality, meaning that you have to fit a certain, that specific curve. We still want symmetry to be a requirement. So when the population of differences is close to normal, the signed rank test is less likely to reject a false null hypothesis than a t-test. So there's some disadvantage to this guy as well. That's why non-parametric tests are not done widely, and only done when necessary. So there are ranks used here too. So the Wilcoxon signed rank test is based on what we call signed ranks for the paired differences to rank the values. Basically what you do, and we'll do an example of this as well, you compute the differences to get one sample. So you find the difference between, sample A and sample B and get one group of differences. You compute the absolute values of those differences, and then you rank the absolute values of those differences, ignoring any differences of 0. So if you get a difference of 0, you just ignore it. It doesn't get ranked. Any ties should have the values assigned the average of the corresponding ranks, just like before. So the tie thing still works. And then we would give each rank a plus or minus sign according to the sign of the difference it corresponds to. And once you've done that, you would compute the sum of the positive ranks and the sum of the negative ranks. The smallest value, ignoring the negative sign, is the value of the test statistic used to see if there is a difference. There are special tables for this test, which is why we're not going to do it by hand. We're going to let R do the work for us. So let's take a look at how we might do the rankings when we have signed ranks. A group of 8 individuals with high cholesterol levels participated in an exercise program that was designed to lower cholesterol levels. Cholesterol levels in milligrams per deciliter were measured before and after exercise for each individual with the following results. So we've got our data of before and after here. I went ahead and calculated the differences to save us a little bit of time. So that -7 came from taking 283 minus 290. The 18 here came from doing 299 minus 281, so forth and so on. Okay. And so then we took the absolute value of the ranks. That was kind of one of the steps in the procedure. And so now we have them all absolute values, and now we have to put the actual ranks to them first and foremost. So I'm going to go through the absolute value ranks first of all and see how many of them I have that are the same value here, okay, of the absolute values. So it looks like I have a pair of 12s. And it looks like I have the rest of them are all different, so that's good to know. So we need to rank them first in order from smallest to largest. 3 looks like it's the smallest, so it gets a rank of 1. 2 for the absolute value 5. That's the second largest value, and the absolute value row there. 6 would be the third largest. 7 looks like it's the fourth largest. And then your two 12s would be 5 and 6 respectively. And then 18 is 7, and then 26 is 8. So remember, the ones where there's no ties between the two, between the data values and the ranks, are given the same values below. So got 1. I'm going to go ahead and pull them down here. 1, 2, 3, 4. Now the fifth one here and here, 5 and 6 had the same data value difference. In other words, they both had a difference of 12 in the absolute value, so they get the same rank. So 5 and 6 will both get a 5.5. And then the remaining don't have any ties, so they just get 7 and 8. So those are the ranks we're dealing with. Now we have to go back through and give a negative sign to wherever the original difference was negative. So the original differences were negative here, here, here at -5, and that -12. So all those will get negative signs attached to their signed rank here at the end. So that'll be a -4, -1, -5, -5.5. They get the signs that go with them. So the rest of them will remain positive because their original values were positive. So what they would actually do here, if you were doing, you'd have your negative ranks and the positive ranks, and you would sum those guys up. And as the test over here, or the last portion here on the previous slide stated, we need to compute the sum of the positive ranks and the sum of the negative ranks. The smallest value, ignoring the negative sign, would be the value of our test statistic. So over here, if we did the negative ranks, we're going to have -4 plus -1 plus -2 plus -5.5 for the negative ranks. For the positive ranks, we've got 7 plus 5.5 plus 8 plus 3. I'm willing to bet the negative ranks are going to be the smaller of the two. That's -12.5. Let me double check my arithmetic here. And this is 23.5. So you look at them ignoring the negative sign from the negative ranks, and the one with the smallest value would be your test statistic, and this would be the test statistic in this case. But we don't have the table to go off of to find the p-value, so it's not very meaningful to us here, and we'll stop with that example there. I just wanted to show this to you. I do not want you to do this if you run this test. Okay? But what I do want you to do is the following. Step 1, again, we're going to perform the assumption checks as we would do for a paired samples t-test. We're going to run the QQ plots and Shapiro test on the differences. We'll find the differences first, and then we'll find we'll run the QQ plot on those differences in the Shapiro to see if they're normal or not. If they are normal, that means the assumptions are met, and we should go ahead and just do a paired samples t-test. If those differences show non-normal behavior, then we're going to run the Wilcoxon sign rank test, and we'll move on to step 2. So to state the null and alternate hypothesis for the Wilcoxon sign rank test, you'll have the null hypothesis, the median of the differences, the population median of the differences is equal to 0, versus the median of the differences for the alternative is not equal to 0. So basically a two-tailed test. Most people use this test specifically to do a two-tailed test. It's rare you see a greater than or less than version in this one. But it can be done. I'm not saying it can't be done, but it's just rare to see it done. So we'll stick with the two-tailed test for this, just to see if there's a significant difference between the two groups. We'll still use the Wilcox.test function in R, and we'll use the paired equals true in one of our arguments to check for the significant differences between our groups and then write a conclusion. So that being said, let's run one of these suckers real quick. So in example 2 here, and in the study on effects of caffeine in myocardial blood flow, measured in milliliters per minute per gram, 10 subjects had their blood flow measured before, they call this the baseline, and after consuming caffeine. So that's going to be our caffeine group. Perform the appropriate hypothesis test to see if there is a difference on the median myocardial blood flow before and after consuming caffeine. So obviously this is paired data because you've got 10 subjects who you tested their blood flow beforehand and then gave them caffeine and tested them afterwards to see if there was a difference there. So in R, we're going to get the baseline and the caffeine data in there, and then we're going to create a vector called D for differences, or if you want to call it diff, I don't care. But it's going to be your baseline minus your caffeine scores. Now, I am going to have you guys do one of these specifically on the project. So if I ask you to do this test specifically, I'm only going to ask you to do one. It'll either be the Mann-Whitney test or the Wilcoxon sign rank test. But if I ask you to do this test, then I'm going to want you to get the data in there and then compute the differences. Like so. So you get the data in there for baseline and caffeine, and then you create your vector of differences equals baseline, not base and B, baseline minus caffeine. Alright, and then if you're doing this in R Markdown, make sure you put the D at the very end and hit enter so it spits out the differences. That's how I can check to see that you did things correctly as far as getting the data in there. Those are the differences we want to see if they're normal or not. So in the second step of this, we will do a QQ norm plot and the Shapiro test on that alone. So I'm just going to show you this because at this point we kind of know how to use the QQ norm, QQ line, and Shapiro test functions in R. But notice that my first entry into each one of these is that vector I built of differences I just called D. Okay. The Shapiro test gives a value that's below 0.10, so 0.08, small enough to say it's not normal. But then when we look at the line, it kind of looks like it's doing this. It's very wavy and kind of offshoots from the side. If it wasn't for that one outlier, we may barely get a normal distribution or a very approximate normal distribution. It's not the worst looking plot we've seen by far this semester, but the points do seem to veer from the line. So, and that Shapiro test value 0.08 being smaller than 0.10, we can say the differences are not normal, and we should probably do the Wilcoxon sign rank test. So this, if it was more normal looking, we'd want to do a paired t-test here, but since it's not, we're going to do the Wilcoxon sign rank test. Okay. So in R to run that Wilcox.test, we're going to use very similar notation to what we did the first time we ran it from the Mann-Whitney U, with the exception of the following. I'm going to run the Wilcox.test. I'm going to put baseline in first, caffeine in second, alternative equals 2-sided, paired equals true, and the other two things I've got exactly as I had them before. The only thing I really changed was I added paired equals true here and made sure my alternative reflected what I'm going to run when I do this test. All right. So ultimately, what we wanted to find from this test was when we wanted to have our null hypothesis that the difference of the medians, or the difference of the two medians, is equal to 0. In other words, there's no difference. Versus the alternative, which is the median of the differences is not equal to 0. In other words, there is some kind of difference. And when I run that test in R, I get a value of 0.0322, which is between 0.001 and 0.05. So we do have some evidence that there's a difference between the baseline and caffeine here. So all we can really say here is that since P is between 0.001 and 0.05, we reject the null hypothesis. There is strong evidence that the median myocardial blood flow differs before and after consuming caffeine, which we kind of would expect. Caffeine usually has a pretty good effect on blood flow in general. So we'd hope that would come out to be substantial here. It may not be in all cases, but it is in this. Now again, you could get a confidence interval here if you so chose. So that's how I would have been if I'd have ran that. But if I'd have changed the one thing here, confidence interval conf.int equals to t for true, it would spit me out a two-sided interval. And notice that they're both positive here, which implies that at baseline our blood flow was the myocardial blood flow measurements were greater in both of these cases here. So in this case, we'd say we were 95% confident that the median myocardial blood flow for at baseline is greater than that of caffeine by at least 0.04 and at most 0.71 milliliters per whatever that measurement was. It was milliliters per minute per gram. Okay, so if you really wanted to do it, I'm not going to really request that you do confidence intervals for these, but if you wanted to do them, you can. And I just wanted you to know that. And so that is it, gang. And that's all I'm going to teach you this semester. I hope everybody learned something, and hope everybody's doing good. Talk to you guys later.